Look up at the night sky, and you'll see our moon, a familiar, steady companion hanging there in the darkness, lighting our paths and pulling our tides. It feels constant, eternal, like it's always been exactly where it is. But what if that isn't the full story? What if the moon we see today isn't the only one that ever graced our skies? Imagine for a moment ancient civilizations gazing upward, not at one moon, but two or maybe even more. Moons that have since vanished, lost to the immense and mysterious workings of our solar system. It sounds like science fiction, but what if it wasn't? What if some of these celestial bodies simply disappeared? This is the incredible mystery we're exploring today, the missing moons. Throughout human history, myths and legends from cultures around the world have hinted at multiple moons lighting up the night, stories often dismissed as pure imagination. But modern astronomy is starting to reveal that there might be more truth to these ancient tales than we ever realized. Cosmic events of almost unimaginable scale, collisions, captures, ejections could have reshaped our solar system in ways that erased entire moons from existence. Some may have crashed into planets, others could have been flung out into deep space, lost forever. And if that's true, what did our ancestors really see when they looked up? You're about to join a journey far beyond the ordinary, a deep dive into one of astronomy's most compelling puzzles. We'll explore cutting-edge research, re-examine long-forgotten myths, and follow the clues scientists are using to piece together the history of our cosmic neighborhood. This isn't just a story about rocks in space. It's a search for lost worlds, a reimagining of human history, and a chance to see the sky through the eyes of those who came before us. So settle in, open your mind to the possibilities, and let's venture together into the mystery of the missing moons. Our solar system today is a well-mapped neighborhood, at least in broad strokes. We know Earth has one moon, a singular, rocky companion. Mars has two small, irregularly shaped moons, Phobos and Deimos, often thought to be captured asteroids. Then you have the gas giants, which are like miniature solar systems unto themselves. Jupiter boasts an incredible 92 known moons, from the massive Ganymede, larger than the planet Mercury, to a swarm of tiny, captured asteroids. Saturn, with its stunning rings, also has over 80 confirmed moons, including the enigmatic Titan with its thick atmosphere and methane lakes. Even the ice giants Uranus and Neptune have their own collections of satellites, each with unique characteristics. This modern census didn't just appear overnight. It's the result of centuries of observation and, more recently, the incredible data sent back by space probes. And with this knowledge comes a framework for how scientists believe these moons came to be. There are three primary ways a planet gets a moon. The first is through accretion, where moons form from the same swirling disk of gas and dust that the planet itself forms from, essentially growing up together as a system. The second method is capture, where a planet's gravity seizes a passing object, like an asteroid or a Kuiper belt object, and pulls it into a stable orbit. The third, and perhaps most dramatic, is the giant impact hypothesis, the leading theory for our own moon's formation. This suggests a Mars-sized object slammed into the young Earth, and the debris from that colossal collision coalesced in orbit to form the moon we see today. For the most part, these orbits are considered stable over astronomical timescales, lasting for billions of years. The delicate gravitational dances between a planet and its moons, and even between the moons themselves, create resonant patterns that can lock these orbits into place, making them predictable and enduring. This stability is a cornerstone of our understanding, allowing us to model the solar system's past and future with a high degree of confidence. It paints a picture of a system that, while dynamic in its youth, has settled into a predictable rhythm. But what if this picture of stability is incomplete? What if the calm, ordered system we see now is merely the quiet after a much more chaotic and violent storm? Yet for all our modern understanding, a fascinating question lingers. Has our solar system always looked exactly like this? To find an answer, we must turn back the clock, not with computer simulations, but by looking into the oldest records of humanity itself. Ancient civilizations across the globe were not just myth makers. They were the first rigorous scientists, dedicated sky watchers who meticulously tracked the heavens and left behind a legacy of astonishing precision. Their observations, carved into clay tablets, painted on tomb walls, and encoded in complex calendars, may hold cryptic clues to a very different cosmic past. Consider the Babylonians, master astronomers who operated out of Mesopotamia over 2,000 years ago. Their clay tablets, inscribed with cuneiform script, don't just contain simple stories, they are complex mathematical diaries. They recorded lunar and planetary movements with such accuracy that their data is still used by modern astronomers to study things like the gradual slowing of Earth's rotation. But some of their texts are more enigmatic. Certain tablets reference celestial events or stars that behave unlike any known planet or star we can identify today. They speak of lights in the sky that appeared, performed a journey, and then vanished. While often interpreted as comets or supernova, the precise descriptions of motion and duration sometimes defy these easy explanations, leaving a tantalizing opening for other possibilities. Meanwhile, in ancient Egypt, the sky was a direct reflection of their divine realm. The ceiling of the tomb of Senenmut, an advisor to Queen Hatshepsut, contains one of the oldest known star charts. It depicts the constellations with remarkable accuracy, but its celestial figures also include a mysterious second disk near the representation of the moon in some interpretations. While mainstream Egyptology views this as a complex religious symbol, perhaps representing a deity, its persistent presence alongside the unmistakable moon has fueled speculation. Could it be a symbolic memory passed down through generations of a time when two luminous objects shared the night sky? Perhaps the most compelling and precise records come from the Maya of Mesoamerica. Their Dresden Codex, a bark paper book, is a breathtaking work of astronomical mathematics. They calculated the cycles of Venus with an error of just 1 day in 500 years and understood the lunar month with similar precision. Their entire culture was governed by the rhythmic, predictable dance of celestial bodies. This makes their references to a lost or dark moon all the more intriguing. Some scholars point to passages that seem to describe a lunar cycle that doesn't align with our single moon, hinting at a time of different astronomical relationships. For a culture that built its civilization on accurate timekeeping, such an anomaly in their records is a powerful clue that cannot be easily dismissed. These aren't just isolated curiosities. Cultures separated by vast oceans and millennia often share surprising common threads. Native American tribes like the Chumash of California have oral histories that tell of a time before our current moon, describing a previous, brighter satellite that met a cataclysmic end. In the writings of the ancient Greek philosopher Anaxagoras, we find accounts based on even older sources that speak of other bodies orbiting Earth, long before our moon was known to do so. So what are we to make of all this? It's easy to dismiss these stories as pure mythology, the fanciful inventions of pre-scientific cultures, but that view is increasingly seen as arrogant and simplistic. These ancient astronomers possessed sharp, unaided eyesight and a patience that modern humanity has largely lost. They spent their lives watching the sky, noting every slight variation, every change in brightness, every deviation in path. Their survival often depended on it. To assume that they consistently and universally misidentified common objects like comets or planets requires a greater leap of faith than to simply consider that they might have been recording exactly what they saw. Their collective testimony points to a possibility that our night sky, for all its apparent permanence, may have once hosted other travelers since lost to time. Of course, the very stability we take for granted in our solar system is a dynamic equilibrium. a delicate balance of forces that, if disturbed, can lead to dramatic and permanent change. To understand how an entire moon could vanish, we need to shift our perspective from a static map to a dynamic, gravitational battlefield where celestial bodies are in a constant state of push and pull. The mechanisms for disappearance aren't science fiction. They are fundamental processes dictated by the laws of physics, and we see evidence of them happening all across the cosmos. One of the most common ways a moon could be lost is through a gravitational slingshot, a dramatic event known as ejection. Imagine a complex dance between a planet and several moons. Their orbits can fall into what's called a resonance, where their orbital periods are ratios of each other, like one moon orbiting twice for every single orbit of another. This can create regular, repeating gravitational tugs. Normally, these interactions are stable, but if the system is perturbed, perhaps by a close pass from a rogue planet or a large asteroid, that delicate balance can be shattered. The gravitational kicks between the moons can add up, transferring energy. One moon might gain so much velocity that it reaches escape velocity, breaking free of the planet's gravitational grip entirely. It would be flung out of the system, becoming a rogue moon drifting alone in the cold, dark interstellar void. We suspect this is the fate of many early moons around the giant planets. Their chaotic youth was likely a game of gravitational pinball, ejecting countless smaller bodies. Then there's the far more violent and final option, collision. In the early solar system, the space around young planets was a crowded and chaotic construction zone, filled with planetesimals and debris. The odds of a direct impact were immensely higher than they are today. A moon on a stable orbit could have its path altered by a gravitational nudge, sending it on a new trajectory that intersects with another moon or even its host planet. The result is utter obliteration. A moon-on-moon collision would shatter both bodies into a cloud of dust and rubble, which might eventually reform into a new, single body or scatter to form a ring system. We see echoes of this in the oddly shaped moons of Saturn and Uranus, which look like they were pieced together from the fragments of much larger, ancient predecessors. A direct impact with the planet itself would be even more cataclysmic, leaving behind perhaps only a massive basin or a unique elemental signature in the planet's crust as a tombstone. A slower, more grinding fate is tidal disruption. This process relies on the relentless tug of a planet's gravity. A moon that orbits too close to its planet experiences an intense gravitational gradient. The planet pulls much harder on the side of the moon facing it than on the far side. This stretches the moon, and if it ventures inside what's known as the Roche limit, this tidal force becomes stronger than the gravitational force holding the moon itself together. The moon is literally ripped apart. It doesn't vanish in an instant, but over time, it's shredded into a ring of particles, its material slowly raining down on the planet or spreading out into a new orbital disk. We see this process in action today. Mars's moon Phobos is slowly spiraling inward and is expected to be torn apart by tidal forces in tens of millions of years, potentially giving Mars a new ring as a grim souvenir. Finally, a moon might not vanish so much as be stolen. In a solar system crowded with massive planets, a close encounter can lead to a capture event, but in reverse. A large planet like Jupiter, with its immense gravity, could effectively hijack a moon orbiting a smaller neighbor. A precise gravitational interaction during a close pass could rob the smaller planet of its satellite, transferring the moon into a new orbit around the gas giant. From the perspective of the original planet, its moon has simply disappeared without a trace, captured by a gravitational thief in the night. This could explain some of the irregular moons with retrograde orbits around the giant planets. They are likely captured asteroids, but the same mechanism could have stolen larger bodies in the past. These aren't just theoretical ideas. We have a potential case study right in our own celestial backyard. The leading theory for the formation of our own moon, the giant impact hypothesis, implies the violent destruction of a planetary body often called Theia. If that impact had happened slightly differently, the debris might not have coalesced into a new moon. It could have been ejected entirely or fallen back to Earth, leaving us with no moon at all. This shows us that the presence of our moon is the result of a very specific set of circumstances, a cosmic roll of the dice. If it happened here, it undoubtedly happened elsewhere, and not every roll was a winner. Some planets likely lost their moons in the chaotic game of solar system formation, and the evidence of those lost satellites may be hidden in plain sight, encoded in the orbital patterns of what remains or buried deep within the geological record of the planets themselves. This collective memory of a different sky isn't confined to any one continent. Journey to the Arctic Circle, and you find the Inuit people with a rich tradition of celestial lore. Their stories speak of a time when the moon was brighter and closer, a time before it was struck by a great force and dimmed, retreating to its current, colder distance. In the dense rainforests of South America, the Disana people of the Amazon tell of a celestial war among the gods, a conflict that shattered a second moon, scattering its fragments across the heavens to become the stars of the Milky Way. These narratives, separated by thousands of miles and years, share a common thread, a profound celestial change, a disruption in the established order of the night. But how could such a memory persist across generations without a written language? The answer lies in the power and purpose of oral tradition. For ancient cultures, these stories were not mere entertainment. They were the living textbooks of their people, encoded with vital knowledge about the world, history, and survival. Elders would pass these tales down with meticulous care, ensuring each detail was preserved. The rhythm, the repetition, and the very structure of these myths were designed for accurate memorization. A change in the sky, an event as monumental as the disappearance of a moon, would have been a cataclysmic event seared into the collective consciousness. It would become a central pillar of their worldview, a story told and retold around countless fires, its truth embedded in the very fabric of their culture. It's less a matter of perfect historical recall and more one of preserving a profound, transformative truth about their reality. This doesn't mean we should take every myth literally. The language of mythology is one of symbol and metaphor, where cosmic events are often personified as gods and giants. A story about a moon being eaten by a sky wolf could be a dramatic retelling of a lunar eclipse. A tale of a war in heaven could symbolize the gravitational chaos of planetary migration. The kernel of truth isn't necessarily in the specific characters, but in the underlying event. The sudden absence of a light, a great collision, a lasting change in the heavens. These stories are the ancient human attempt to rationalize and document the inexplicable, to make sense of a universe that behaved in terrifying and unpredictable ways. When we listen to these myths with this perspective, they transform from simple fables into potential historical documents, the first eyewitness accounts of our solar system's turbulent youth. They suggest that the calm, predictable sky we gaze upon today might be a recent chapter in a much longer and more violent story. Our ancestors may have been the last witnesses to a different cosmic arrangement, and they passed down what they saw in the only language they had. The question then becomes not if these events happened, but which specific celestial mechanic, a collision, an ejection, a capture, each ancient story is trying to describe. The legends provide the clue. Our task is to decipher its true meaning. Now, let's turn our attention to a world much closer to home, a planet that serves as a perfect and deeply puzzling case study for these very theories of cosmic change, Mars. The red planet, with its two bizarre little moons, Phobos and Deimos, presents a mystery that has persisted since their discovery. These aren't the kind of large, spherical moons we'd expect to see orbiting a planet like Mars. Instead, they're small, lumpy, and scarred, looking more like potatoes than proper satellites. Their very existence challenges our standard models and forces us to ask a critical question. Are we looking at captured asteroids, or are we seeing the lonely survivors of a much larger, lost lunar family? The conventional explanation, the one you'll find in many textbooks, is the capture theory. The idea is that Phobos and Deimos originated in the asteroid belt between Mars and Jupiter. Billions of years ago, a complex gravitational dance with the young, growing planets could have sent them hurtling inward on new paths. As they passed close to Mars, the planet's gravity seized them, pulling them into orbit. This theory seems to fit their appearance. Their irregular shapes, low density, and dark, carbon-rich composition are strikingly similar to asteroids found in the outer belt. It's a neat and tidy answer, but modern research has begun to pull at its threads, revealing inconsistencies that are hard to ignore. The first major problem is their orbits. Both moons orbit Mars in nearly perfect, stable circles that are almost exactly aligned with the planet's equator. This is highly unusual for a captured object. Think of it like this: catching a passing asteroid with gravity is a messy, violent process. It typically results in a highly elliptical, tilted orbit, anything but the pristine, circular paths we observe. To get these moons into such tidy orbits through capture alone would require a series of incredibly precise and unlikely gravitational maneuvers, a celestial billiard shot of almost impossible perfection. It's not impossible, but it starts to feel like a stretch. This orbital perfection points toward a different origin story, one intimately tied to Mars itself. What if Phobos and Deimos didn't come from the asteroid belt, but were born from Mars? This leads us to the impact hypothesis. We know Mars was bombarded by giant asteroids in its early history. The planet's scarred southern hemisphere is a testament to that violence. A gargantuan impact, much like the one that formed Earth's moon, could have blasted an enormous cloud of Martian debris into orbit. This debris would have quickly coalesced into a large single moon. But the story doesn't end there. The gravitational influence of the Sun would have then begun to tug on this new moon, creating a drag effect that slowly caused it to spiral inward. As this progenitor moon drifted closer to Mars, it would have eventually crossed the Roche limit, that point where a planet's tidal forces overpower the gravity holding a moon together. The result would have been catastrophic. The immense moon would have been torn asunder, shattered into countless pieces. Most of that material would have crashed onto the Martian surface in a spectacular shower of destruction, but some of the fragments could have remained in orbit. Over time, the gravitational interactions between these pieces would have caused them to coalesce again, but not into one large body. Instead, they formed the two small, rubble pile moons we see today, Phobos and Deimos. This theory elegantly explains their circular equatorial orbits. They formed from a disk of debris around Mars and their low density, as they're not solid rock but loose collections of rubble. And the evidence for this drama isn't just theoretical. Recent spectral data from probes like the ESA's Mars Express suggests the surface composition of Phobos doesn't perfectly match any known class of asteroid. Instead, it shows signs of minerals that could have originated on Mars itself. Furthermore, the grooves and lines scarring the surface of Phobos look less like impact craters and more like stretch marks, fractures caused by the tidal forces that are, right now, slowly pulling it apart. Phobos is continuing its inward death spiral, getting 6 feet closer to Mars every century. In tens of millions of years, it too will cross the Roche limit and be destroyed, likely creating a temporary ring around the planet before its material rains down. This isn't just a story about the past, it's a cycle that is still playing out. This raises a profound and thrilling possibility. If Mars once had a larger moon that was destroyed, could it have had even more? The dynamics of such a catastrophic breakup are chaotic. It's entirely plausible that the initial disintegration created not 2, but several moons. The gravitational environment around Mars is weak, and smaller moons would have been highly unstable. They could have easily collided with each other and merged into Phobos and Deimos, or been perturbed by the Sun's gravity and ejected from orbit entirely, cast adrift to become rogue asteroids, or perhaps even captured by Jupiter's immense gravity well. The two moons we see today may simply be the last remnants of a larger, more complex lunar system that has since been lost to time and gravity, a silent echo of a more crowded Martian sky that ancient terrestrial observers might have just been able to glimpse. But if the story of Martian moons hints at a dynamic past, the realm of Jupiter reveals a system of almost unimaginable scale and chaos. As the largest planet in our solar system, Jupiter is a gravitational titan, a cosmic vacuum cleaner whose immense pull has shaped the entire architecture of the planetary neighborhood. Its current collection of 92 known moons is a diverse family, from the four massive Galilean satellites Ganymede, Callisto, Io, and Europa, down to a swarm of tiny, captured asteroids often just a few kilometers across. This isn't a static collection, it's a bustling, ever-changing traffic circle where moons are constantly arriving, departing, and sometimes meeting their end. Jupiter's gravity is so powerful that it doesn't just hold onto its moons, it actively sculpts the environment around it, capturing objects that wander too close. The space near the gas giant is filled with countless planetesimals, asteroids, and cometary nuclei. Any one of these could, given the right trajectory, be snared by Jupiter's gravity and forced into a temporary orbit. Modern computer simulations of the early solar system show this process in action, revealing that gas giants like Jupiter likely had a much larger retinue of small, irregular moons in their youth. These weren't permanent additions, many were on unstable paths from the very beginning. Their orbits would decay, or they would receive a gravitational kick from a larger moon, sending them spiraling inward to be consumed by the planet's thick atmosphere or slingshotted back out into the depths of space. This constant churn suggests a fascinating possibility that Jupiter's moon count has never been a fixed number. Instead, it may represent a transient population with moons coming and going over billions of years. Some of these captured objects might have only stayed for a few thousand or million years, a mere blink in geological time, before moving on. The ones we see today are simply the long-term survivors, the objects that managed to find a stable orbital niche amidst the gravitational turbulence. The rest, the temporary moonlets, have vanished without a trace, their brief tenures leaving no obvious mark on the current system. So how do we find evidence for something that is no longer there? Astronomers turn to the intricate patterns within the system itself. The orbits of Jupiter's current irregular moons are not random. They cluster into distinct groups based on their inclination and eccentricity. Each group is thought to be the remnant family of a single larger captured object that was shattered by an impact after being captured. The fragments from that breakup would share similar orbital characteristics, just as we see today. This implies that the number of captured objects was once smaller, but each one was larger, and that the current swarm of tiny moons are the debris from those primordial destruction events. Some of the original parent bodies may have been truly substantial, perhaps even rivaling the size of the larger irregular moons we see today, only to be lost to collisions that we can now only infer from the evidence left behind. The gravitational influence of the Sun also plays a crucial role in this chaotic ballet. For moons orbiting far from Jupiter, the Sun's gravity becomes a significant perturbing force. It can slowly tug on these distant satellites, altering their orbits over immense timescales and eventually providing enough energy to liberate them from Jupiter's grasp. This process could have steadily eroded the population of outer moons, ejecting them to become solitary nomads traveling between the stars. These ejected moonlets would join the vast population of interstellar objects like Oumuamua or Borisov that we are only beginning to detect as they pass through our modern solar system. Every such visitor could, in theory, be a lost moon from another star or even an ancient refugee from Jupiter's own chaotic past, finally returning on a long, looping journey. The grand conclusion from studying Jupiter is that moon systems, especially around gas giants, are not museums displaying pristine relics from the solar system's birth. They are active, dynamic, and sometimes violent environments. Moons are acquired, modified, and lost through a continuous process governed by gravity. The stability we perceive is an illusion of our brief human timescale. Over the eons, the cast of characters in Jupiter's sky has undoubtedly changed, with countless temporary satellites making brief appearances before their gravitational dance led them to a final exit, either into the crushing depths of the planet or out into the infinite cold of interstellar space. But the story of cosmic destruction and rebirth doesn't end with the solitary fate of a single moon. For the most stunning possible evidence of this cycle, we must travel outward to the jewel of our solar system, Saturn. Its magnificent rings are one of the most iconic sights in all of astronomy, a breathtaking halo of ice and rock that has captivated observers for centuries. For a long time, their origin was one of the great mysteries. Were they leftover material from the planet's formation that simply never coalesced into a moon? Or could they be something far more dramatic, the glittering, silent graveyard of a moon that once was? The idea that these rings are the remnants of a destroyed moon is not only compelling, it's supported by a growing body of evidence. The rings are almost pure water ice, remarkably clean and bright, which suggests they are not primordial. Leftover material from the birth of the solar system would be darkened and polluted by billions of years of dust accumulation. Their pristine condition points to a much more recent origin, geologically speaking, perhaps within the last 100 million years. This timeline opens the door to the possibility of a relatively recent celestial catastrophe. Mathematical models provide a stunningly clear picture of how this could happen. Imagine a mid-sized moon, similar to Saturn's moon Mimas, orbiting the planet in a stable path. Over immense timescales, the gravitational interactions with Saturn and other moons could ever so slowly alter its orbit, causing it to migrate inward. This is a common process. We see it happening with moons across the solar system. As this doomed moon spiraled closer to the immense pull of Saturn, it would eventually cross that fatal boundary known as the Roche limit. Inside this zone, the planet's tidal forces the difference in gravity between the side of the moon facing Saturn and the side facing away becomes stronger than the gravitational force holding the moon together. The result is not a sudden explosion, but a methodical gravitational unraveling. The moon is systematically stretched and pulled apart. First, it might deform into an egg shape, then begin to shed material from its outer layers. Eventually, the entire structure fails, shattering into countless fragments. These pieces, ranging in size from tiny grains to massive mountain-sized chunks, would not immediately crash into the planet. Instead, they would spread out along the orbital path of their parent moon, their individual collisions and gravitational interactions grinding each other down into smaller and smaller particles. What was once a single, cohesive world becomes a vast, flat disk of debris, a new ring system. This theoretical process finds its echo in the incredible data sent back by the Cassini spacecraft. Its grand finale orbits, diving between the planet and its rings, gave us an unprecedented look at the structure and composition of this celestial wonder. The findings were revelatory. The mass of the rings was determined to be much lower than some older models predicted, consistent with the disintegration of a moon no larger than Mimas. Furthermore, the rings are still actively evolving. Cassini observed phenomena like ring rain, where tiny particles are being pulled by gravity into Saturn's upper atmosphere. This suggests the rings are not a permanent feature, but a temporary, dynamic structure that is slowly draining away. We are witnessing a system in flux, a beautiful and ephemeral monument to a moon that sacrificed its unity to create one of the most spectacular sights in the heavens. The question of timing becomes absolutely fascinating. If the rings are indeed the result of a destroyed moon, when did this happen? Some estimates, based on the pollution rate of the rings, suggest they could be as young as 10 to 100 million years old. This is a mere eye blink in the 4.5 billion year history of the solar system. It means that while dinosaurs roamed Earth, Saturn may have had an additional moon that was in the process of being torn apart or had just recently met its end. The light from this cataclysm would have taken over an hour to travel across the solar system, invisible to any earthly eyes. Yet, the aftermath is now a crown we can see with even a small telescope. This theory transforms our perception of the rings from a static painting into a dynamic, ongoing story. They are not simply there, they are happening. We are not looking at a fossil, but at an active crime scene billions of miles across, with the evidence still glittering in the sunlight. It suggests that the architecture of planetary systems is not fixed in stone, but is subject to sudden and violent revision. The peaceful, ordered solar system we see today might be a snapshot of a temporary calm between episodes of cosmic chaos. Saturn's rings stand as a breathtakingly beautiful reminder that even moons are not forever, and that from the ashes of destruction, the universe can create its most stunning works of art. To truly grasp how moons could simply vanish, we have to journey back to the very beginning, to a time before the planets as we know them even existed. Picture this: 4.6 billion years ago, our solar system wasn't a serene collection of worlds in orderly orbits. It was a chaotic, violent construction zone, a vast cloud of gas and dust swirling around a newborn star. Within this protoplanetary disk, dust grains began to stick together, colliding and accreting into ever larger chunks, first pebbles, then rocks, then mountain-sized planetesimals. This was an era of relentless chaos, a gravitational free-for-all where countless objects vied for space, their paths constantly crossing in a high-stakes celestial dance. This period, known as the Late Heavy Bombardment, was the solar system's most violent chapter. For hundreds of millions of years, the inner planets were pummeled by an unimaginable rain of asteroids and protoplanets. The scarred, cratered face of our moon stands as a silent witness to this apocalyptic era. Every impact crater we see on the moon, on Mercury, and on Mars tells a story of a near miss for Earth, a cataclysm that reshaped entire worlds. In this environment, the very concept of a stable orbit was a temporary luxury. For any moon that managed to form around a young planet, survival was never guaranteed. Their existence was a fragile balance, constantly threatened by the gravitational pull of passing giants or the shattering impact of another rogue body. Consider the process of moon formation itself. While some moons coalesced gently from disks of material around their planets, many were likely born from incredible violence. The leading theory for our own moon's origin, the giant impact with a Mars-sized body called Theia, is a perfect example. That collision was so titanic it vaporized part of the early Earth and hurled a disk of molten debris into orbit. In the aftermath, our moon slowly assembled itself from that wreckage, but this scenario wasn't unique to Earth. Similar giant impacts must have occurred around other planets, each one potentially creating a new family of moons. However, not every collision was so creative. For every moon-forming impact, there were undoubtedly countless others that were purely destructive, shattering nascent satellites or blasting them clear out of their orbits. The young gas giants Jupiter and Saturn were the ultimate gravitational powers in this turbulent nursery. Their immense pull acted like a cosmic pinball machine, flinging smaller objects in every direction. A moon peacefully orbiting a smaller planet like Mars or even a young Earth could have its path utterly disrupted by a close pass from one of these giants. The gravitational encounter could either catapult the moon out of the solar system entirely, sending it on an eternal journey through interstellar space, or send it careening inward on a new, fatal trajectory toward the Sun or another planet. The solar system was a dynamic and dangerous place, where the gravitational influence of the largest bodies constantly reshaped the fates of the smallest. Within this maelstrom, stability was the ultimate prize. The moons we see today, from our own familiar companion to the dozens orbiting Jupiter and Saturn, are not necessarily the ones that formed first or were even the largest. They are simply the survivors, the ones that managed to find a stable orbital niche amidst the chaos. They avoided catastrophic collisions, resisted gravitational perturbations from passing bodies, and settled into resonant, predictable paths with their planetary hosts and sibling moons. Their survival was a matter of luck, location, and orbital dynamics. For every moon that survived, countless others may have been lost, shattered into rings, consumed by their planets, or exiled into the deep freeze of interstellar space. This perspective completely changes how we view our cosmic neighborhood. The solar system we study today is not a pristine museum exhibit frozen in time. It is the aftermath, the quiet, settled state following an epoch of unbelievable violence and change. The peaceful harmony of orbiting planets and moons is a recent development, a calm that has descended after billions of years of turmoil. The missing moons are the ghosts of this chaotic past, their absence a silent clue to the dramatic events that shape the worlds we see today. By understanding the violent processes of the early solar system, we begin to see that the question isn't really, where did the moons go? But rather, how did any of them manage to stay? This journey into the chaotic past of our solar system brings us to one of the most compelling pieces of evidence for planetary capture, a world so strange it seems to defy the very rules of its neighborhood, Neptune's moon, Triton. While most large moons orbit their planets in an orderly fashion, moving in the same direction as the planet's rotation, Triton is a spectacular rebel. It orbits Neptune backwards or in a retrograde motion, a clear sign that it was not born alongside the ice giant, but is an outsider that was seized by its immense gravity. This single, bizarre moon offers a stunning window into the dynamic and often violent rearrangements that have shaped planetary systems, revealing a history where even the largest satellites were not immune to being uprooted and captured. The evidence for Triton's captured status is overwhelming and written in the fundamental laws of its motion. In our solar system, planets and their moons predominantly formed from a single, spinning disk of gas and dust. This shared origin story means almost everything spins and orbits in the same direction, a state known as prograde motion. Triton's retrograde orbit is a glaring violation of this rule, a powerful indicator that it originated elsewhere and was pulled into its current path later. Its orbit is also highly inclined and perfectly circular, characteristics that are incredibly difficult to achieve through capture. This suggests that after being captured, Triton's orbit was gradually circularized and tidally locked over billions of years, a process that would have generated immense internal heat and likely melted its interior, potentially creating the liquid ocean that scientists suspect exists beneath its icy crust today. So where did this massive interloper come from? The prevailing theory points its origin toward the Kuiper belt, that vast ring of icy bodies beyond Neptune's orbit that is home to dwarf planets like Pluto. Triton's composition, a mix of rock and ice, is a perfect match for other large Kuiper belt objects. The most likely scenario is that Triton was once part of a binary system, two objects orbiting each other as they traveled through the outer solar system. During a close encounter with Neptune, the planet's gravity could have disrupted this delicate dance, capturing one member of the pair, Triton, while slingshotting its companion away into a new path, perhaps sending it deeper into the Kuiper belt or even ejecting it from the solar system entirely. This gravitational hijacking would have been an event of incredible precision and power, forever altering the destiny of this frozen world. The capture of Triton would have been an apocalyptic event for any original moons Neptune might have possessed. Before Triton arrived, Neptune likely had a system of smaller, native moons that formed with the planet, orbiting peacefully in prograde motion. The arrival of such a massive object on a chaotic, retrograde path would have been utterly disruptive. Triton's gravity would have violently perturbed their orbits, creating a celestial demolition derby. Some of these primordial moons would have been sent crashing into each other, shattering into clouds of dust. Others would have had their orbits so severely altered that they were flung into Neptune itself, burning up in its atmosphere, or ejected entirely from the Neptunian system, cast adrift to become rogue objects in the freezing darkness of interstellar space. Triton, in a sense, is a moon that conquered a world, wiping out any previous lunar family to claim its place as the sole dominant satellite. This dramatic history forces us to reconsider the very nature of moon systems across the cosmos. If a planet as large as Neptune can have its original satellite family completely erased and replaced by a captured dwarf planet, then no moon's position is truly secure. Triton stands as a monumental example of planetary system mobility, proving that gravitational capture isn't just a theory for small, asteroid-like moons. It can happen to worlds large enough to be planets in their own right, fundamentally reshaping the architecture of a planetary system billions of years after its formation. This single moon is a fossil record of the solar system's chaotic youth, a testament to the fact that the peaceful order we see today was forged in a crucible of gravitational chaos, where entire worlds were stolen, destroyed, and rearranged on a cosmic scale. This brings us to one of the most dramatic and well-supported stories of cosmic creation, the origin of our own moon. The prevailing theory, known as the giant impact hypothesis, paints a picture of almost unimaginable violence that ultimately gave rise to the serene companion we see today. The story begins with the early solar system, a chaotic and crowded place where dozens of protoplanets jostled for space in overlapping orbits. Among them was a young, still molten Earth and a Mars-sized body scientists have named Theia. The orbits of these two worlds eventually intersected, leading to a collision of cataclysmic proportions. This was not a simple sideswipe, it was a direct, obliterating impact. Theia struck the early Earth with such force that it is believed to have vaporized on impact, while simultaneously shearing off a massive portion of our planet's mantle and hurling it into space. The energy released would have been beyond comprehension, momentarily turning Earth into a spinning sphere of incandescent magma. The debris from this apocalyptic event, a mixture of material from Theia's core and Earth's own mantle, was thrown into a furious, orbiting disk of vaporized rock, encircling our planet like a seething hot ring. In the cooling aftermath, gravity began to work its magic. Within just a few hundred years, this disk of debris started to coalesce, with particles clumping together into larger and larger bodies. These moonlets, or lunar embryos, quickly swept up the remaining material, and within about a century, the primary building blocks of our moon had formed. Over the next 100 million years, this new satellite settled into its stable orbit, becoming the single, large moon we know today. This theory elegantly explains several key observations. The moon's composition is strikingly similar to Earth's mantle, particularly in its relative lack of heavy iron and volatile elements. The heavier iron from both impactors would have sunk into Earth's core during the event, while the lighter mantle material was ejected. It also accounts for the angular momentum of the Earth-Moon system, and provides a reason for the moon's relatively large size compared to its host planet, a ratio unique in the inner solar system. But this specific, almost perfect outcome was the result of a very precise set of circumstances. The angle of the impact, the size of Theia, and the velocity of the collision all had to fall within a remarkably narrow range to create a single, large moon instead of a ring of debris or multiple smaller satellites. It was a cosmic roll of the dice that came up in our favor. This naturally leads to a profound and thrilling question. If it happened here, why wouldn't it have happened elsewhere? The early solar system was a shooting gallery, and giant impacts were not rare events. They were the fundamental mechanism of planetary growth. It is statistically near certain that other planets, particularly Venus and Mars, experienced their own giant impacts with protoplanets of similar or even larger size. The outcomes of these collisions, however, would have been wildly different based on the specific conditions. A slightly faster impactor, a different angle of collision, or a strike on a planet with a different rotational speed could have yielded a completely different result. A planet like Venus, for instance, which rotates backwards incredibly slowly, may have suffered a colossal impact that effectively put the brakes on its rotation and wiped out any initial moon system it might have had. Alternatively, an impact could have created a temporary disk of debris that coalesced into one or even multiple moons, but why don't we see them today? The gravitational environment around a planet is complex. For any moons that formed, long-term stability was not guaranteed. The gravitational tug of the Sun, especially on planets closer to it like Venus and Mercury, can act as a powerful destabilizing force over billions of years. Moons born from these ancient cataclysms could have slowly spiraled inward due to tidal interactions until they crossed the Roche limit and were torn apart, their material crashing back onto the planet's surface. Or a gravitational nudge from a passing planetesimal could have ejected them from orbit entirely, casting them adrift into the solar system to be captured by another planet or become lonely interstellar travelers. So how do we search for evidence of these lost lunar families? The clues are subtle but not invisible. For a moon that spiraled inward and collided with its planet, the evidence would be a massive planet-wide anomaly. Geologists searching for signs of Theia's impact on Earth look for isotopic signatures in ancient rocks, but for a later moonfall event, the evidence would be a global layer of material deposited in a relatively short time frame. A signature that might be incredibly difficult to find after billions of years of geological recycling. Another clue lies in a planet's rotational tilt or obliquity. A giant impact or the later loss of a large moon can dramatically alter a planet's spin axis. The extreme axial tilt of Uranus, for example, which essentially rolls around the Sun on its side, is widely believed to be the result of one or several colossal impacts in its past. While we don't know if that created temporary moons, it shows the scale of violence that was possible. The most promising place to look might be in the precise orbital characteristics of any remaining moon. If we find a system of moons that seems too perfectly arranged, it could be the surviving core of a much larger family, with the missing members having been ejected through gravitational interactions. The study of orbital resonances where moons tug on each other in stable, repeating patterns can be used to run computer simulations backwards in time, testing whether the current arrangement could have evolved from a previous, more populated state. Each moon we see today might be the sole survivor of an ancient celestial battle, a witness to a time when the night sky above its planet was lit by multiple satellites, all since vanished through the relentless and unforgiving workings of gravity. This gravitational relationship between a planet and its moon is far from static. It's a dynamic, evolving dance that can fundamentally alter their fates over immense timescales. This process is known as tidal evolution, and it's driven by a subtle but relentless force, the gravitational tug of war that creates a slight bulge on both the planet and the moon. Think of it like this: the moon's gravity pulls on the planet, stretching it slightly into an oval shape. Conversely, the planet's gravity does the same to the moon. These aren't dramatic, ocean-sized bulges, but incredibly slight deformations in the very rock of the worlds themselves. The magic and the consequence comes from the fact that these bulges don't sit perfectly aligned. Because the planet is spinning on its axis, it actually rotates a little bit faster than the moon orbits around it. This means the planet's tidal bulge is always being dragged just a tiny bit ahead of the point directly under the moon. That forward-pointing bulge now has its own gravitational pull, and it tugs on the moon, giving it a slight nudge forward in its orbit. This constant nudging transfers a little bit of the planet's rotational energy to the moon, pushing it into a gradually wider, slower orbit. This is what we see with our own moon. It's moving away from Earth at a rate of about 1.5 inches every year. But this story can have a very different ending depending on the specific dynamics of the system. For some moons, the opposite happens. They spiral inward on a collision course with their planet. This fate is dictated by the relative spin rates. If a moon orbits the planet faster than the planet spins on its axis, the situation reverses. The planet's tidal bulge lags behind, and its gravitational pull now acts as a brake on the moon, sapping its orbital energy and causing it to drift slowly closer. This is the current reality for Mars's moon Phobos. It's trapped in this inward spiral, destined to be torn apart by Martian gravity in tens of millions of years. The ultimate outcome of this inward journey is destruction. As the moon gets closer, the difference in gravitational pull across its body, the tidal force, becomes exponentially stronger. Once it crosses that invisible boundary known as the Roche limit, the planet's gravity overwhelms the moon's own self-gravity. The moon can no longer hold itself together. It undergoes tidal disruption, being systematically ripped apart into a stream of debris that will eventually form a magnificent ring system, a fleeting monument to a world that once was, much like we theorize happened at Saturn. There's a third, more subtle path a moon can take on this gravitational journey: ejection. This is less about a direct tug of war between two bodies and more about the complex interplay within a system of multiple moons. When moons orbit in resonant patterns, for example, one moon completing exactly 3 orbits for every 2 of another, they give each other periodic gravitational kicks. These interactions can sometimes add up, transferring energy in a way that doesn't just change an orbit, but massively accelerates one moon. If it gains enough velocity, it can reach escape velocity, breaking free of the planet's grasp entirely to be flung out into the lonely expanse of interstellar space, becoming a rogue moon wandering the galaxy. This process of gravitational scattering is likely how the giant planets lost many of their smaller, early moons, cleaning up their celestial neighborhoods and leaving behind only the most stable survivors we see today. This delicate gravitational balance finds its breaking point at a concept known as the Roche limit, a celestial boundary that marks the difference between a moon's survival and its spectacular demise. Named after the French astronomer Édouard Roche, who first calculated it in 1848, this isn't a physical barrier you can see, but a precise mathematical distance from the center of a planet. Inside this zone, the tidal forces we just discussed, the difference in a planet's gravitational pull on the near and far sides of a moon, becomes stronger than the gravitational force that holds the moon itself together. It is, quite simply, the point where a planet's gravity starts to win the tug of war against a moon's own self-gravity. To visualize this, picture yourself holding a small ball of loose gravel. As long as you hold it gently, the gravel stays together, bound by its own minuscule gravity and friction. But if you were to start spinning it rapidly in your hand, the centrifugal force would eventually overcome that weak binding force and the gravel would fly apart. A planet's tidal forces act in a similar way on a moon that ventures too close, stretching it and pulling until its structural integrity fails. For a large, solid moon made of rigid rock, the Roche limit is very close to the planet. But for a smaller moon, or one that is a fragile collection of rubble loosely held together, a rubble pile, this fatal boundary is much farther out, making it far more vulnerable to tidal disruption. We don't have to look far to find moons dancing dangerously close to this edge. Within Saturn's magnificent rings, small moonlets like Pan and Atlas orbit astonishingly close to the planet, well inside the traditional Roche limit for a solid body. The reason they haven't been torn apart is a testament to their unique composition. These are not solid, monolithic rocks. They are thought to be highly porous aggregates of ice and dust, often referred to as rubble piles. Their internal strength comes not from the gravitational bond between particles, but from their inherent material strength and friction, the same way a sandcastle can hold its shape against gravity. Their very existence, skimming so close to destruction, helps astronomers refine their understanding of the Roche limit, showing it's not a single hard line but a complex region influenced by a moon's density, rigidity, and internal structure. The real question is whether any moon has ever crossed this threshold, and the evidence suggests a resounding yes. The most stunning and widely accepted example is the very origin of Saturn's rings. The prevailing theory posits that a former moon, perhaps as large as the planet's current moon Mimas, spiraled inward over millions of years due to tidal interactions. As it crossed the Roche limit, Saturn's gravity began to peel it apart layer by layer. This wouldn't have been a single, instantaneous explosion, but a gradual, systematic unraveling, a celestial spool of thread being unwound into orbit. The moon's material was distributed along its original orbital path, creating the vast, flat disk of ice and rock we see today. The incredible purity of the ring ice supports this. It hasn't been darkened by billions of years of cosmic dust, hinting at a relatively recent destruction in the last 100 million years or so. But Saturn's rings might not be the only tombstone for a lost moon. The asteroid belt between Mars and Jupiter is filled with fragments, and some astronomers speculate that certain families of asteroids could be the remnants of a moon that was shattered, either by a colossal impact or by tidal forces during a close pass by a young, still-forming Jupiter. Furthermore, the peculiar and highly tilted orbits of some of the distant irregular moons around the gas giants could be the survivors of a much larger population that was gravitationally perturbed, with their less fortunate siblings being nudged inward across the Roche limit to be devoured by the planet. The process of tidal destruction is likely a recurring theme in the life of a planetary system, a fundamental mechanism that continuously recycles material, turning moons into rings and eventually, perhaps, feeding that material back into the planet itself in a final, fiery rain. So how do astronomers transform from passive observers into cosmic detectives, searching for evidence of celestial crimes that occurred billions of years ago? They cannot travel back in time to witness a moon's destruction or capture, so they must rely on indirect clues, building their case piece by piece with a sophisticated toolkit of modern scientific methods. This detective work often begins not with a telescope, but with a supercomputer, where researchers build intricate digital models of the solar system's violent past. These computer simulations are like virtual time machines. Scientists input all the known laws of physics, gravity, orbital mechanics, the physics of collisions, and populate this digital universe with thousands, sometimes millions, of virtual planetesimals, asteroids, and protoplanets. They then run the simulation forward over billions of years of compressed time, watching to see how this chaotic cloud of material self-organizes. The goal is to see if the natural processes of accretion and collision naturally produce a solar system that looks like our own. Often they do not. These models frequently show that the calm system we see today is an unlikely outcome unless it experienced a period of dramatic instability, an event known as the Nice model, where the giant planets migrated, scattering countless objects and utterly reshaping the architecture of the outer solar system. Within these digital recreations, astronomers watch moons form, migrate, and meet their end. They see how often moons are gravitationally ejected from their planets or pulled inward to be tidally shredded. By running these simulations thousands of times with slightly different starting conditions, they can identify which outcomes are mere flukes and which are statistically inevitable. If 99 out of 100 simulations show that a young Jupiter must have ejected a significant number of its early moons to arrive at its current configuration, that becomes powerful circumstantial evidence that such moon loss events did in fact happen. The computer becomes a laboratory for testing theories of lunar disappearance, providing a plausible history written in lines of code and gravitational equations. But a good detective needs physical evidence, not just a theoretical model. For that, scientists turn to the most enduring records in the solar system: impact craters. The surfaces of airless worlds like Mercury, our moon, and the moons of the outer planets are museums of impact history, preserving a record of collisions stretching back billions of years. The pattern, size, and frequency of these craters can tell a sophisticated story. A sudden, intense spike in cratering on a moon like Callisto or Iapetus could indicate a period of incredible instability, perhaps when a neighboring moon was shattered, sending a hail of debris across the system. By carefully dating these surfaces, planetary geologists can potentially link a wave of impacts across multiple moons to a single, catastrophic event: the break-up of a large moon. The geology of the planets themselves can also hold clues. A moon that spirals inward and collides with its planet wouldn't just leave a crater. It would deliver an enormous amount of material, potentially creating a unique geochemical signature in the planet's crust. Scientists searching for evidence of Theia's impact with Earth, for example, look for subtle differences in the ratios of certain isotopes in ancient rocks. Similarly, if a large, icy moon from the outer solar system had been captured and then destroyed by a gas giant, it might have deposited water and other volatiles deep in the planet's atmosphere, leaving a faint but detectable trace that could be spotted by a probing spacecraft. Perhaps the most elegant detective work involves studying the survivors, the moons that are still here. Their current orbits are a frozen record of their past gravitational interactions. Astronomers can mathematically rewind the clock, calculating how their orbits have evolved over time due to tidal forces. This process can reveal astonishing histories. For instance, the moons of Uranus have orbits that are currently very stable, but running the tidal equations backwards suggests they have not always been that way. Their paths hint at a past filled with chaotic orbital resonances that could have easily ejected smaller sibling moons from the system, clearing out any smaller satellites that once shared their space. The orbital resonances between moons are like echoes of past conversations. When moons have orbital periods that are simple ratios of each other, like Jupiter's moons Io, Europa, and Ganymede, which are in a 1:2:4 resonance, it indicates a long, slow dance of gravitational nudges that has pushed them into this stable configuration. But getting into this lockstep often requires clearing the gravitational neighborhood. The process of achieving these resonant orbits can violently destabilize the paths of any other moons that are not part of the club, often leading to their ejection or collision. The very perfection of these resonant chains is itself evidence that other, less fortunate moons were once present and have since been removed from the picture. Every irregular moon with a tilted, backward orbit around a gas giant is a witness for the prosecution in the case of the missing moons. Their captured status proves that the process of lunar acquisition and loss is ongoing. By studying the orbits of these captured moons, scientists can often trace their paths backward to identify their likely origin points in the asteroid belt or Kuiper belt. This helps build a statistical understanding of how many objects a planet's gravity can capture over its lifetime, and by extension, how many it might have also lost. The current population is just a snapshot. The true number of moons that have ever graced a planet's sky is almost certainly far, far greater than the ones we see today. This multi-pronged approach, combining theoretical simulations, geological analysis, and precise orbital mechanics, allows astronomers to piece together a history that is not written in any book. They are forensic scientists at a crime scene 4.6 billion years old, gathering fingerprints, analyzing blood spatter patterns, and reconstructing the sequence of events from the faintest of traces. Each line of evidence reinforces the others, building a compelling case that our solar system's past was a dynamic and often violent place, and that the familiar, solitary moon hanging in our night sky is the exception, not the rule, in a cosmos where celestial companions are often gained and just as often lost. Yet for every moon ejected into the lonely dark, there remains a possibility of discovery, a chance that these lost satellites did not entirely vanish but found a new home in the solar system's final frontier, the Kuiper Belt. This vast disk of icy bodies, stretching from Neptune's orbit out to immense distances, is far more than just a collection of primordial leftovers. It is a cosmic graveyard and a refugee camp, a place where worlds exiled by the gravitational turmoil of the inner solar system may have finally come to rest. Here, amidst the frozen dwarfs like Pluto and Haumea, we might just find the fingerprints of those missing moons. The process of how an object from the inner solar system could end up here is a complex gravitational ballet. When a moon is ejected from, say, Jupiter's grasp, it doesn't simply fly straight out into interstellar space. Its path is still curved by the sun's gravity, and it often enters a highly elliptical, unstable orbit that brings it swinging back through the planetary zone. With each pass, the giant planets can give it another gravitational kick, either sealing its fate as an interstellar traveler or, crucially, nudging it onto a less eccentric path that settles into the distant, stable reservoir of the Kuiper Belt. This process, known as gravitational scattering, is how many comets are thought to reach the Oort cloud, and it could equally well apply to larger, moon-sized objects. This leads to a fascinating possibility. Some of the Kuiper Belt objects we've already discovered might not be native to that region at all. They could be captured moons, planetary interlopers that originated around the giant planets billions of years ago. The challenge is identifying them. A captured moon would have a composition different from the primordial ice rock mix of most Kuiper Belt objects. It might be denser, richer in specific minerals, or have a different internal structure, clues that could only be uncovered by a close-up visit from a spacecraft. Their orbits might also hold clues, paths that are unusually inclined or have parameters that are difficult to explain through in situ formation alone, hinting at a dramatic past involving a close encounter with a giant planet. Even farther out lies the most speculative and tantalizing repository, the Oort cloud. This is a hypothetical spherical shell of icy objects surrounding the solar system at a distance of up to a light year away, so far that the sun appears as just a particularly bright star. Gravitational interactions with passing stars and the galactic tide can occasionally dislodge one of these objects, sending it falling inward as a long-period comet. But woven into this vast population could be a small number of much larger bodies, true lost moons that were ejected with such force that they reached this ultimate resting place. These would be the most difficult objects to find, as they reflect almost no sunlight and would be virtually invisible with current technology. Their discovery would rely on detecting their subtle gravitational influence or by sheer luck as one of them begins its multi-million-year journey back toward the inner sun. The search for these lost moons is more than just a celestial scavenger hunt. It's a direct investigation into the solar system's violent adolescence. Finding a captured moon in the Kuiper Belt would be like finding a fossilized bone from a previously unknown creature. It would instantly reshape our understanding of the past. It would provide concrete evidence for the dynamic models of planetary migration and moon ejection, moving them from compelling theory to observed fact. By studying its composition, we could learn about the conditions around the young Jupiter or Saturn, environments we can never directly observe. Each such discovery would add a crucial piece to the puzzle, helping us write the true history of our cosmic neighborhood, a story written not in books, but in the orbits and compositions of worlds waiting to be found in the frozen dark. But to truly grasp the scale of what might be possible, we must expand our view beyond our own solar system and look to the stars. The study of exomoons, moons orbiting planets in other star systems, is revolutionizing our understanding of lunar formation and stability. While no exomoon has been definitively confirmed yet, the very hunt for them and the theoretical models built to support that search are revealing just how dynamic and chaotic moon systems can be across the cosmos. The theories we've built from studying Jupiter, Saturn, and Triton are being stress-tested in laboratories of the imagination, applied to environments far more extreme than anything we have at home. Consider the most common type of planet we've found beyond our solar system, the hot Jupiter. These are gas giants that orbit blisteringly close to their parent stars, completing a full revolution in just a few days. According to our traditional models of solar system formation, gas giants are supposed to form in the cold, outer regions of a protoplanetary disk. Their presence so close to their star implies a dramatic history of planetary migration, an inward spiral that would have had catastrophic consequences for any moons that dared to follow. As a hot Jupiter migrates inward, the intense tidal forces from the star would have ripped away its entire lunar family. Any moon that wasn't immediately ejected or shredded would have had its orbit destabilized beyond recognition. The very existence of these planets suggests that entire moon systems can be completely erased during a planet's journey. Yet, some daring theories propose that exomoons might not just be destroyed, they could also be born from this chaos. A gas giant moving inward would plow through a dense region of the protoplanetary disk, potentially capturing immense amounts of material that could coalesce into new moons during the migration process. Furthermore, the incredible gravitational forces at play could tear apart other planets or large planetesimals, creating disks of debris around the hot Jupiter from which new satellites could form. This means an exomoon orbiting a hot Jupiter might not be a primordial object at all, but a second-generation world born from the wreckage of the planetary system's violent reorganization. Its composition and orbit would tell a story completely unlike that of any moon in our solar system. The potential diversity of these distant moons is staggering. We could find exomoons larger than Earth, so-called supermoons orbiting gas giants in the habitable zone of their star, where temperatures might allow for liquid water and just maybe the conditions for life. The gravitational interplay in such a system would be incredibly complex, with the moon experiencing intense tidal forces not only from its planet but also from the star. This could lead to extreme volcanic activity or a subsurface ocean kept warm by constant gravitational flexing, making it a prime candidate in the search for extraterrestrial life. The discovery of such a world would instantly redefine the cosmic prospects for life, shifting the focus from planets to their possibly far more numerous and diverse moons. The methods for detecting these distant moons are as ingenious as the theories predicting them. Astronomers look for subtle signs in the data as a planet transits or passes in front of its host star. They search for additional dips in starlight that could indicate a moon trailing or leading its planet. They also look for slight variations in the precise timing of a planet's transit. If a planet has a large moon, the gravitational tug of war between them will cause the planet to wobble slightly, making its transits occur a few seconds early or late. This transit timing variation method is like detecting the faintest whisper of a moon's gravity from hundreds of light years away. What we are learning from this entire endeavor is a profound lesson in cosmic humility. Our solar system, with its relatively stable and well-behaved moons, might be the exception rather than rule. The exoplanet era has revealed planetary systems that defy our simple classifications, with planets orbiting binary stars, planets with diamond clouds, and worlds with orbits more elliptical than any in our Sun's family. It is only logical that their moon systems would be equally bizarre and dynamic. The study of exomoons suggests that our own solar system's history of lunar capture, ejection, and destruction was not a unique trauma, but a common part of planetary adolescence across the galaxy. Every new observation pushes us to reimagine the past, not just of other stars, but of our own sun, and to consider that the quiet, familiar sky we see today is but a single, peaceful frame in a much longer and more turbulent cosmic film. This period of unimaginable cosmic violence, known as the Late Heavy Bombardment, stands as one of the most pivotal and destructive chapters in our solar system's early history. Roughly 4 billion years ago, long after the planets had first coalesced, the inner solar system was suddenly and violently revisited by a cataclysmic rain of asteroids and comets. This wasn't the gentle accretion of the initial formation era. This was a true lunar apocalypse, a period of sustained chaos that would have utterly reshaped the surfaces of young worlds and likely determined the fate of any early moons that had managed to form. The evidence for this bombardment is written across the face of our own moon. The lunar highlands, those bright, heavily cratered regions, are the scar tissue from this event. By counting these craters and using radiometric dating on Apollo mission rock samples, scientists have pinned this intense period to a relatively narrow window between 4.1 and 3.8 billion years ago. The leading theory to explain this delayed chaos is the NICE model, which suggests the giant planets Jupiter and Saturn underwent a dramatic orbital migration. As they shifted their positions, their immense gravity scattered a vast reservoir of leftover planetesimals, flinging them inward like gravitational shrapnel toward the terrestrial planets. The inner solar system became a shooting gallery, and every world was a target. For any moons orbiting Earth, Venus, or Mars during this time, survival would have been a matter of sheer luck. A direct impact from a large planetesimal could have shattered a small moon completely, vaporizing it or breaking it into fragments that would either crash onto the planet or be ejected from orbit. Even a near miss could have been devastating. The gravitational perturbation from a massive object passing nearby could have destabilized a moon's orbit, sending it on a new path that crossed the Roche limit of its planet, leading to tidal disintegration, or giving it enough velocity to escape the system entirely. It's entirely plausible that Earth or Venus once had small, primordial moons that were simply blasted away during this bombardment, their existence erased from the geological record. Yet from this destruction, new moons could also have been born. A giant impact on a planet, much like the one that formed our moon with Theia, could have been triggered during this period. A colossal strike on Venus or early Mars could have blasted sufficient material into orbit to form a new lunar companion. The debris from such an impact would have initially formed a ring of molten rock, which would then have coalesced into one or several moonlets. However, the environment was so chaotic that the long-term stability of any new moon was far from guaranteed. It could have been struck again, shattered by a subsequent impact, or its orbit destabilized before it could settle into a permanent, stable relationship with its planet. The bombardment didn't just affect the planets, it also resurfaced the moons themselves. Any large moon existing at the time, like our own, had its entire crust remodeled. The relentless impacts broke up the surface, creating the vast basins that would later be filled by volcanic lava, flows to become the dark Maria or seas we see today. The heat from these impacts could have also triggered profound internal changes, melting subsurface layers and potentially initiating or altering geological activity. A moon's entire destiny, whether it became a geologically active world or a dormant fossil, may have been decided by the random pattern of impacts it endured during this violent epoch. This period of chaos forces us to view the solar system not as a static arrangement, but as a dynamic system that underwent a severe stress test. The late heavy bombardment was likely the final act of planetary formation, a great clearing out that removed the last of the construction debris in the most dramatic way possible. The moons we see today, including our own, are the survivors of this cosmic trial by fire. They are the ones that withstood the barrage, avoided a fatal gravitational nudge, and found a stable orbit in the calm that followed the storm. Their continued presence is a testament to their resilience, and their scarred surfaces are a permanent archive of the solar system's most violent era. Imagine the solar system not as a silent void, but as a grand concert hall where planets and moons are musicians in a gravitational orchestra. Each body exerts a subtle pull on the others, and when their orbital rhythms sync up in perfect mathematical harmony, we get a phenomenon known as orbital resonance. This is the music of the spheres, a delicate, invisible dance that can create breathtaking stability or unleash absolute chaos, often determining whether a moon remains a permanent part of a planet's family or is cast out into the darkness forever. A resonance occurs when the orbital periods of two moons form a simple whole number ratio. For instance, one moon might orbit its planet exactly twice for every single orbit of another, creating a 2-to-1 resonance. Every time the inner moon completes 2 laps, the outer moon completes 1, and they end up in the same relative position, giving each other a consistent gravitational tug. These repeated, predictable interactions can lock the moons into incredibly stable, long-lasting patterns that protect them from wild orbital changes. It's a harmonious gravitational handshake that keeps the system orderly. However, this same beautiful mechanism has a destructive twin. If the system is perturbed, that same rhythmic nudging can become a destructive feedback loop. Instead of gentle tugs that maintain balance, the moons begin to give each other violent gravitational kicks. Energy is transferred between them, much like one pendulum transferring its momentum to another. One moon can gradually gain orbital energy, pushing it into a higher, slower orbit, while the other loses energy and falls inward. If this process continues unchecked, the inner moon can be driven so close to its planet that it faces tidal destruction, or the outer moon can gain so much energy that it reaches escape velocity, breaking free of the planet's gravity entirely to be flung out of the system as a rogue object. We see a stunning example of stable resonance in Jupiter's inner large moons, Io, Europa, and Ganymede. They are locked in an exquisite 1-2-4 orbital resonance. For every single orbit Ganymede completes, Europa completes exactly 2, and Io completes 4. This precise rhythm creates a gravitational harmony that has maintained their orbits for billions of years. Their resonant relationship is so perfect and stable that it actually helps keep their paths predictable and prevents them from colliding or being ejected, a masterclass in celestial coordination. But this stable configuration likely came at a cost. Astronomers running sophisticated computer models of the early solar system have found that for Io, Europa, and Ganymede to have fallen into their current resonant lock, their orbits must have migrated inward over time in a process driven by tidal forces. As they migrated, their changing gravitational influences would have violently cleared their orbital neighborhood. Any smaller, earlier moons that shared their space would have been destabilized by these shifting giants. Their paths would have been thrown into chaos, likely leading to collisions that shattered them into dust or gravitational interactions that ejected them from the Jovian system entirely. The very perfection of the resonance we see today is evidence of a prior demolition job, a gravitational cleansing that left only the largest survivors in a stable arrangement. The absence of other large moons in the inner Jupiter system is a silent testament to this turbulent past. The region is now neatly ordered by the resonant giants, but it hints at a history that was far more crowded. The gravitational symphony played by Io, Europa, and Ganymede is a beautiful piece of music, but its opening movements were likely incredibly violent, a dramatic overture that cleared the stage for the stable performance we observe today. This demonstrates the dual nature of orbital resonances. They can be the architects of long-term order, but they often first act as wrecking balls, removing any objects that don't fit into their new harmonic structure. While the solar system's history is filled with tales of moons being captured or destroyed by outside forces, some of the most fascinating disappearances might have come from within. Imagine a moon spinning peacefully for eons, suddenly beginning to wobble, its rotation growing faster and faster until the centrifugal force overcomes its own gravity, and it simply splits in two. This isn't science fiction, it's a legitimate, though controversial, theory known as rotational fission, and it offers a compelling explanation for how a single moon could vanish, only to be replaced by several smaller successor bodies. The underlying physics is surprisingly intuitive. Think of a figure skater pulling their arms in to spin faster. As their mass moves closer to their axis of rotation, their spin rate increases due to the conservation of angular momentum. Now apply that to a celestial body. If an event like a massive impact causes a moon to contract or shed its outer layers, its spin could dramatically accelerate. If that rotation becomes fast enough, the moon can no longer hold itself together. It doesn't necessarily explode. Instead, it undergoes a process of fission, where a chunk of its mass is literally spun off into a new, independent orbit, creating a binary moon system or even a cloud of debris that could later coalesce into new satellites. It's a mechanism for creating new moons from the breakdown of an old one, a celestial act of reproduction through dissolution. We may even have a potential example of this process in its earliest stages right here in our solar system. The distant Pluto-Charon system is often cited as a possible product of a giant impact, but some of its characteristics also hint at a complex rotational history. More strikingly, the asteroid duo Antiope, located in the main belt, consists of two nearly identical-sized bodies orbiting each other. Their similar composition and density strongly suggest they were once a single object that fissioned into two, providing a small-scale, real-world model of how this process can work. If it can happen to an asteroid, it's not a giant leap to suggest it could have happened on a much larger scale to a primordial moon in the distant past. This leads us directly to the asteroid belt itself, a region often considered a graveyard of planetary building blocks. Many of the asteroids we observe aren't solitary rocks. They have their own tiny moonlets orbiting them. For a long time, the assumption was that these were captured debris, but an increasingly compelling theory suggests that at least some of these asteroid moon systems are actually families, the surviving fragments of a larger parent body that was torn apart. A catastrophic collision between two asteroids could certainly shatter one into pieces, but so could rotational fission if the asteroid was spun up too fast, perhaps by the subtle but relentless pressure of sunlight, an effect known as the Yorp effect. Identifying these breakup events requires some brilliant cosmic detective work, and the clues are written in the compositions and orbits of the objects left behind. When a larger body breaks apart, whether by impact or fission, the fragments will share an almost identical composition. So, if we find a binary asteroid pair where both members have matching spectral signatures, meaning they're made of the same mix of minerals and ices, it's a powerful hint that they originated from the same source. Furthermore, their orbits can tell a story. The dynamics of how they move around each other can be run through simulations to see if their current paths are consistent with a recent separation from a single object. The most convincing evidence, however, might be found not in the asteroids but on the surfaces of the moons we can study up close. If a large moon was torn apart by tidal forces or rotational fission, the event would have been spectacularly violent, sending a hail of debris across its entire planetary system. This shrapnel would have bombarded every other moon in the vicinity. A geologist looking at the surface of a moon like Callisto or Iapetus might find a layer of craters all dating to the same specific period in history. If the chemical signature of the impactor material in those craters was consistent across the entire system and matched the composition of a remaining moon like, say, Hyperion, it would be a smoking gun evidence that Hyperion is a surviving fragment of a much larger body whose destruction left its mark on every other satellite in the sky. We are, in a very real sense, reading the solar system's history through the scars left on its survivors. While the stories and theories are compelling, the search for lost moons must ultimately move beyond ancient texts and computer models to the hard, observational evidence gathered by our robotic emissaries in space. For decades, unmanned probes have been our eyes and ears throughout the solar system, and the torrent of data they've sent back contains subtle clues that could finally confirm these celestial disappearances. Some of the most intriguing hints come from a world we know intimately, our own moon. The Lunar Reconnaissance Orbiter, or LRO, has been meticulously mapping the lunar surface in incredible detail since 2009. While its primary mission is to scout future landing sites, its high-resolution cameras have also revealed a landscape far more complex than a simple, dead world covered in ancient craters. Among its many discoveries are strange, enigmatic features known as irregular mare patches. These are small areas of smooth, seemingly young volcanic rock that appear to have erupted well after the moon's internal geological engine was thought to have shut down. Some estimates suggest they could be as young as 100 million years old, a mere blink in geological time compared to the moon's 4.5 billion year history. The existence of such recent activity is a profound puzzle. A moon's internal heat is generated by the decay of radioactive elements and the leftover energy from its formation. Our moon, being relatively small, should have cooled and solidified completely billions of years ago. So what could have provided a sudden, recent burst of internal heat? One compelling theory points to a massive, late-stage impact. The idea is that a substantial moonlet, perhaps a remnant from the solar system's chaotic past that had shared Earth's orbit, eventually spiraled inward and collided with the moon. The colossal energy from such an impact wouldn't just create another crater. It could have sent seismic shockwaves through the entire lunar body, briefly remobilizing pockets of magma deep underground and forcing them to the surface in these final, isolated eruptions. The irregular mare patches, therefore, might not just be geological curiosities. They could be the scar tissue from the moon's final, fatal encounter with a long-lost sibling. Hundreds of millions of miles away, the Cassini spacecraft performed a masterclass in celestial investigation during its 13 years orbiting Saturn. While its primary target was the ringed planet itself, its detailed study of Saturn's moon system provided a live demonstration of the gravitational processes that can lead to a moon's destruction. Cassini's precise measurements of the moon's orbits confirmed they are actively evolving due to tidal interactions. It found that the moon Enceladus is currently being flexed and heated by its gravitational resonance with the larger moon Dione, powering the incredible geysers that erupt from its south pole. This is a clear, present-day example of how orbital dynamics can directly alter the physical and geological fate of a moon. Most strikingly, Cassini's grand finale orbits provided the most accurate measurements ever of Saturn's gravity field and the mass of its rings. The data revealed the rings are far less massive than some older models predicted, with a total mass consistent with the destruction of a single, icy moon no larger than Mimas. Furthermore, the rings were found to be incredibly young, potentially only 10 to 100 million years old. This timing is crucial. It means the cataclysm that created them occurred while dinosaurs walked the Earth. Cassini didn't just provide a theory for where a moon went. It gave us a time frame for its disappearance and a detailed analysis of the beautiful, glittering debris field it left behind. The mission transformed Saturn's rings from a static icon into a dynamic, evolving crime scene, offering the strongest direct evidence we have that moons can and do vanish. The next great leaps in this detective story will come from the outer solar system, with a fleet of exciting missions planned for Jupiter and its fascinating moons. The European Space Agency's JUICE mission and NASA Europa Clipper are set to arrive at Jupiter in the next decade, and their advanced suites of instruments will be looking for clues of past lunar catastrophes. They will conduct incredibly precise gravitational and magnetic field measurements around Ganymede, Callisto, and Europa, By mapping the subtle variations in these fields, scientists can infer the internal structure of these moons, searching for evidence of massive, ancient impact basins buried beneath the ice or unusual density distributions that could point to a violent, fragmentary origin. Perhaps even more telling will be a close study of the surfaces of these moons. If Jupiter's early history was as chaotic as models suggest, with many small moons being gravitationally ejected or destroyed, the surfaces of the large Galilean moons should bear the marks of that bombardment. The missions will be looking for families of craters that all date to the same era, which could indicate they were caused by the fragments of a single shattered moon. By analyzing the composition of the impactor material preserved in these craters, spectrometers might even be able to match it to the unique makeup of one of Jupiter's current irregular moons, effectively drawing a direct line from a surviving fragment back to the catastrophic event that created it. These missions represent a new era in our quest to understand the solar system's history. We are no longer just cataloging what is there, we are forensically reconstructing what is missing. Every strange gravitational anomaly, every surface scar, and every unusual orbital resonance is a piece of evidence. By combining this data with the powerful testimony of ancient sky watchers and the predictive power of modern simulations, we are slowly piecing together a story of a younger, wilder solar system, a place where the night sky above other worlds was once lit by multiple moons, whose disappearances have left echoes we are only now learning to hear. To truly understand the fate of these lost satellites, we must turn to the most powerful time machines we have, supercomputers running incredibly detailed simulations of our solar system's evolution. These aren't simple video game recreations, they are complex mathematical models that incorporate all the known laws of physics, from gravity and orbital mechanics to the physics of collisions and tidal forces. Researchers can input thousands, sometimes millions, of virtual planetesimals, asteroids, and protoplanets into this digital universe, set the clock to 4.6 billion years ago, and then watch what unfolds over eons of compressed processing time. The goal is to see if the natural, chaotic processes of accretion and gravitational interaction can produce a system that looks like our own, and the results are both illuminating and startling. What these simulations consistently reveal is a history of incredible violence and instability. A young solar system is not a peaceful place, it's a gravitational free-for-all. The models show that the calm, ordered system we see today is actually a highly unlikely outcome. To arrive at our current configuration, the simulations often require a period of dramatic planetary migration, such as the one described by the NICE model, where Jupiter and Saturn shifted their orbits, scattering countless objects and utterly reshaping the entire architecture of the outer solar system. Within this digital maelstrom, the fates of moons are decided in an instant. The simulations show moons being gravitationally captured by passing giants, only to be torn apart by tidal forces shortly after. They show moons on stable orbits receiving a catastrophic gravitational kick from a rogue planetesimal, sending them careening into their host planet or being flung out of the system entirely on a one-way trip into interstellar space. Perhaps the most staggering conclusion from these digital experiments is the sheer scale of lunar loss they suggest. While the percentage varies between models, many simulations indicate that the giant planets Jupiter, Saturn, Uranus, and Neptune may have each possessed early moon populations that were orders of magnitude larger than what we observe today. Some models suggest that for every moon currently orbiting a gas giant, dozens, if not hundreds, of smaller moonlets may have been lost over the eons. These weren't necessarily large, planet-sized bodies, but a vast swarm of smaller satellites, each a temporary gravitational companion that was eventually eliminated through collisions, ejections, or tidal disruptions. The current census of moons in this light represents not the full family, but merely the long-term survivors, the ones that managed to find a stable orbital niche amidst the chaos. The power of these models isn't just in showing that moons were lost, but in revealing the precise mechanisms behind their disappearance. By running the simulations thousands of times with slightly different starting conditions, scientists can identify which outcomes are statistical flukes and which are virtual certainties. For instance, the models show that the process of gravitational scattering, where moons perturb each other's orbits, is incredibly efficient at clearing out smaller bodies. They demonstrate how a large moon migrating inward due to tidal forces can act like a gravitational bulldozer, sweeping its orbital path clean of any smaller satellites, either absorbing them through collision or hurling them away. The simulations provide a plausible, step-by-step history for how a once crowded sky around a planet like Jupiter or Saturn could have been pared down to the more orderly, resonant systems we see today. This virtual detective work is crucial because it provides a framework for understanding the clues we find in the real solar system. The peculiar, tilted orbits of Neptune's captured moon Triton make perfect sense within these models. The existence of Saturn's rings as a recent phenomenon is a predicted outcome. The very fact that Mars's moons, Phobos and Deimos, are so small and orbit so perfectly is elegantly explained by the moon-forming impact and subsequent breakup theory that the simulations help to refine. The computer models act as a bridge, connecting the faint whispers of ancient myths and the hard, observational data from our probes into a single, coherent narrative of a dynamic and ever-changing cosmic neighborhood, where the moons we see are just the last actors left on a stage that was once far more crowded. The surfaces of airless worlds are more than just barren landscapes. They are ancient archives preserving a detailed record of cosmic violence that spans billions of years. Every crater, from the smallest pockmark to the largest basin, is a historical entry, a bullet hole left by a projectile that once wandered the solar system. By reading this pockmarked language, planetary scientists can piece together not just the history of impacts, but also the history of the impactors themselves, including those that have since vanished from our skies. The patterns and distributions of these craters might hold the key to identifying the ghosts of moons long gone. To understand how, we need to think like a forensic scientist at a crime scene. A single crater tells you an impact occurred, but a pattern of craters can tell you about the weapon that was used. A random, uniform distribution of craters of all sizes is the expected result of billions of years of bombardment by asteroids and comets from the asteroid belt and the Kuiper belt. But sometimes, scientists find patterns that break this uniformity: clusters, chains, or strange alignments that defy simple explanation. These anomalies are the clues that point to something more unusual, like the debris from a shattered moon. One of the most telling patterns is a catena or a crater chain. These are straight-line arrangements of craters, often similar in size and equally spaced. We see spectacular examples on Jupiter's moons Ganymede and Callisto. For a long time, their origin was a mystery. They weren't random and they didn't look like volcanic features. The breakthrough came with comet Shoemaker-Levy 9, which was torn into a string of fragments by Jupiter's gravity before colliding with the planet in 1994. This provided a living model. A catena is the signature of a tidally disrupted object, a comet or asteroid that was pulled apart into a line of debris which then struck its target in rapid succession. This immediately raises a compelling possibility. If a comet can be torn apart to create a crater chain, what about a moon? A small satellite that ventured too close to its planet would suffer the same fate, ripped apart by tidal forces into a stream of fragments. This debris would then continue to orbit, eventually intersecting the paths of other moons or even the planet itself. A series of impacts along a single line on a nearby moon would create a catena that acts as a permanent memorial to this lunar death. The crater chains we see on the Galilean moons could therefore be the final resting place of smaller, lost moons of Jupiter that were destroyed in the planet's chaotic past. their existence now only evidenced by the scars they left on their larger, surviving cousins. Beyond clear chains, broader patterns in cratering can also tell a story. Imagine a moon that breaks apart not into a neat line but into a cloud of fragments. This cloud would spread out along its orbital path, creating a temporary, diffuse ring of debris. Any moon that shared a similar orbital inclination would have to periodically pass through this cloud, experiencing a sudden, intense shower of impacts concentrated in a specific band across its surface. This could create a bizarre geological feature, a belt of craters all dating to the same era, encircling the moon's equator or tracing a specific latitude, completely unlike the random peppering seen across the rest of the globe. Finding such a band would be like finding a layer of ash from a specific volcano in ice core samples. It would pin a global event to a specific time. If scientists could date the craters in this band and find they all formed within a relatively narrow window, and if the chemical composition of impactor material trapped in those craters was consistent, it would be powerful evidence for a shared origin. This could point to the catastrophic destruction of a moon that once shared that orbital plane, an event that showered its neighbors with its remains. The surviving moon would carry this belt of scars forever, a dark bracelet etched into its surface to mark the death of a sibling. The search for this evidence is already underway. Planetary geologists meticulously map crater distributions on worlds like Mercury, our moon, and the moons of the outer planets, looking for any statistical deviations from randomness. They look for fields of secondary craters formed by debris ejected from a primary impact, that are themselves unusually large or arranged in a way that suggests the primary impactor was a fragile, rubble pile object, perhaps resembling a moon fragment. They also study the very largest impact basins. The South Pole Aitken Basin on the Moon is one of the largest in the solar system, and the object that created it was colossal. Could it have been a temporary second moon of Earth that eventually spiraled inward and collided in a final, cataclysmic event? While still speculative, the composition of the lunar mantle ejected by that impact, as measured by orbiters, could one day provide clues to the impactor's origin. This line of investigation turns the entire solar system into a crime scene. Every cratered surface becomes a canvas on which the history of missing objects is written. A strange chain on Ganymede, an anomalous band of young craters on Iapetus, or a single massive basin on the Moon. Each could be a clue pointing to the former existence of a moon that orbited for millions of years before meeting a violent end. By reading these cosmic bullet holes, we are not just studying collisions. We are piecing together the population of ancient celestial bodies, including those that are no longer here to tell their own stories. To truly grasp how entire moons can vanish, we must first expand our sense of time far beyond the human scale. Our lives are measured in decades, our history in millennia. But the story of the solar system unfolds over billions of years, a time span so vast it becomes almost abstract. Processes that seem imperceptibly slow to us, the gentle drift of a moon's orbit, the subtle tug of a gravitational resonance, become irresistible, landscape-altering forces when given the near-infinite canvas of deep time. What looks like stability across 1,000 years is merely a single frame in a million-year movie of constant change. Think of it like the erosion of a mountain range. To a person standing at its base, the mountains appear eternal and unchanging. Yet over millions of years, wind and rain slowly reduce those peaks to dust and carry them away to the sea. The mountain's fate is not decided in a single cataclysm, but by the relentless, cumulative effect of countless tiny actions. The disappearance of a moon operates on a similar principle, but the forces at work are gravitational, and the timescales are even more immense. A moon doesn't just pop out of existence. Its fate is sealed by the patient, unyielding hand of gravity, working its will over epochs. We can visualize the solar system's history not as a static portrait, but as a dynamic, evolving film. If we could rewind this film 4.5 billion years, we would see a scene of utter chaos, a swirling disk of gas and dust, with countless planetesimals colliding and merging in a violent dance of creation. The planets themselves are still hot and molten, and their early moon systems are forming amidst this chaos. This is the first act, a time of frequent, colossal impacts where moons are both created and destroyed on a regular basis. The sky above a young Earth or a young Mars might have been lit by several small, irregular moons, their orbits still chaotic and unstable. Fast forward 1 billion years and the scene begins to settle. The major planets have largely cleared their orbital paths, but the late heavy bombardment is raining down the last of the solar system's construction debris. This period is like a violent storm that cleans out the system, and it is likely the death knell for many of those early, fragile moons. A small satellite orbiting too close to its planet could be wiped away by a single direct impact, while a larger one might have its path drastically altered, setting it on a new course that will take hundreds of millions of years to play out, a course that ends in tidal destruction or ejection. By the time we reach the era of the dinosaurs, the solar system looks much more familiar, but the processes of change are far from over. While the inner solar system has become relatively quiet, the giant planets are still dynamically active. Their immense gravity continues to perturb the Kuiper belt, occasionally flinging objects inward, and all across the system, the slow dance of tidal evolution continues unabated. Our own moon is steadily moving away from Earth, and Mars's moon Phobos is continuing its slow, fatal spiral inward. These changes are too slow for any dinosaur or any human civilization to perceive, but they are as inevitable as the rising and setting of the sun. This perspective reveals a profound truth. There is no single, true configuration of the solar system. The arrangement of planets and moons we see today is merely a snapshot, a single moment in a continuous billion-year flow of gravitational interactions. The sky above a planet is a constantly changing exhibit. A world that once boasted 3 or 4 moons might now have only 1 or none at all. Another world, like Saturn, may have recently gained a brilliant ring system from the destruction of a moon that was present for 99% of the planet's history. The calm and order we perceive is an illusion of our brief existence. We are simply living during a peaceful interlude between episodes of cosmic rearrangement. This grand view of deep time transforms the missing moon from a mystery into an inevitability. Given enough time, the subtle becomes monumental and the impossible becomes certain. The gravitational processes that govern moons are not random. They are predictable and relentless. If a moon's orbit is destined to decay, it will decay. If a resonance is destined to eject it, it will be ejected. It is only a matter of time. The solar system has had 4.5 billion years for these processes to run their course, more than enough time for countless moons to have formed, lived, and met their end. Our task is not to wonder if moons disappeared, but to learn how to read the subtle clues they left behind in the orbits of the survivors and the scars on the faces of the planets. While these events paint a dramatic picture of the distant past, a natural question arises. Is the age of disappearing moons over, or are we living in a temporary calm between cosmic storms? The forces that shaped the early solar system have certainly diminished. The chaotic bombardment has ended, and the giant planets have settled into more stable orbits. Yet, the gravitational machinery that can destroy or eject a moon is still very much active, operating on timescales that are both unimaginably long and, in some cases, observable within a human lifetime. Consider the curious case of Neptune's inner moons. This region is a bustling, dynamic place, and the tiny moon Naiad is a perfect example of its strange choreography. Naiad follows a wild, tilted orbit that seems to dance around its neighbor, Thalassa. Their paths are locked in what scientists call a dance of avoidance, a resonant pattern where Naiad's orbit is inclined just enough to repeatedly hop over and under Thalassa's path every time they approach each other. This intricate gravitational two-step prevents a collision, but it highlights the unstable and finely tuned nature of such crowded systems. While not on an immediate path to destruction, Naiad's peculiar motion demonstrates that even today, moon orbits are not set in stone. They are dynamic relationships constantly being adjusted by gravity's invisible hand. For a more direct and impending fate, we need look no further than the fiery future of Jupiter's moon, Io. This is a world caught in a gravitational vise, relentlessly squeezed by its parent planet and its larger sibling moons, Europa and Ganymede. Locked in an orbital resonance, these moons exert a constant, rhythmic pull on Io, generating immense tidal friction within its interior. This is what makes Io the most volcanically active body in the entire solar system. Its surface a constantly changing tapestry of erupting lava fountains and flowing rivers of molten rock. This activity isn't just for show, it represents a massive transfer of energy. While this doesn't mean Io will be torn apart tomorrow, it showcases a moon actively being remodeled by the same gravitational forces that can lead to more dramatic outcomes over longer periods. The most clear and present example of a moon's impending demise is Mars's moon, Phobos. Unlike our own moon, which is slowly moving away from Earth, Phobos is spiraling inward toward Mars at a rate measurable by our instruments about 6 feet closer every century. This inexorable march is driven by tidal forces, and its end is a virtual certainty. In approximately 50 million years, Phobos will cross the Roche limit. When that happens, the weak, rubble pile structure of the moon will be no match for the tidal forces of Mars. It will be systematically torn apart, likely creating a spectacular temporary ring system around the red planet before its debris eventually rains down onto the Martian surface in a fiery shower. For the first time, we are able to monitor a moon on its direct, predictable path to destruction. Beyond our own system, the hunt for Exomoons is teaching us that these processes are universal. The discovery of numerous hot Jupiter exoplanets, gas giants orbiting perilously close to their stars, suggests a history of violent planetary migration. Any moons these giants may have originally possessed would have been stripped away during their inward journey, either torn apart by the star's gravity or ejected into the void. We are also developing the technology to detect the subtle signatures of moon-forming impacts or the faint, dusty rings that could be the remnants of a shattered satellite around a distant star. These observations confirm that the creation and destruction of moons is not a historical relic but an ongoing process throughout the galaxy. So, could we, sitting here in the 21st century, actually witness a moon disappear? The answer is a fascinating mix of yes and no. We will almost certainly not see a large, spherical moon like our own vanish in a single, observable event. Those cataclysms belong to the much longer, slower timescales of cosmic evolution. However, we are already witnessing the prelude to such events. We are tracking the fatal spiral of Phobos. We are monitoring the volcanic death throes of Io. We are mapping the unstable dances of Neptune's inner moons. We are, in a very real sense, watching the opening acts of dramas that will take millions of years to conclude. Our instruments allow us to see the trajectory, to understand the physics, and to predict the outcome. We may not see the final curtain fall, but we have front-row seats to the beginning of the play, understanding the fate of these celestial actors long before they make their final exit from the stage. So as we've journeyed from ancient myths to cutting-edge simulations, from the rings of Saturn to the fragile orbit of Phobos, a profound truth emerges. Our solar system is not a static museum exhibit. It is a living, breathing, and ever-evolving system, a grand celestial dance where moons are not permanent fixtures but temporary partners in a gravitational ballet that spans billions of years. The evidence is compelling and written across the cosmos in the pristine ice of Saturn's rings, a monument to a recently destroyed moon. in the backwards orbit of Triton, a captured invader that wiped out Neptune's original satellites, in the resonant harmonies of Jupiter's moons, whose stability required the ejection of countless others, and in the ancient stories of our ancestors who may have glimpsed a different sky than the one we see today. This ongoing celestial evolution is what makes astronomy such a thrilling and dynamic science. It's a field where the past is constantly being rewritten by new data, and the future holds the promise of unimaginable change. The forces that shaped our cosmic neighborhood are still at work, operating on timescales that dwarf human history but are no less inevitable. Moons will continue to migrate, to be captured, to shatter into rings, and to be flung into the interstellar void. The sky above a planet is an ever-changing canvas, and the current arrangement is merely a single frame in a billion-year film. This perspective invites us all to look up at the night sky with a renewed sense of wonder and curiosity. That familiar moon hanging in the darkness is not just a rock. It's a survivor of a violent and chaotic past, and its presence is a testament to a very specific and fortunate set of cosmic circumstances. The next time you gaze at it, let your imagination wander. Wonder about the celestial companions it may have once had, the moons that danced around Earth or Mars or Saturn before vanishing without a trace. Ponder the cataclysmic events that shaped our system and the silent, patient forces that continue to sculpt it. And perhaps most excitingly, consider what might come next. In 50 million years, will sky watchers on a future Earth look up at a ringed Mars and tell stories of its missing moon? The universe is not a finished product. It is a work in progress, and we are privileged to live in a time when we can finally begin to read its incredible story.